I'm Anil Kumar. Welcome to my series on linear transformations. Now we will look into rotation about origin. So the idea here is to find transformation matrix for rotation about the origin by an angle of theta. So that is the matrix which we are looking forward to, a 2 by 2 matrix which does all the tricks. And if you're following me on this series, you must have understood by now the simplest method to write such a matrix, right? So we'll continue with our simplicity and then see how to create this matrix. So we look into only two components. One is a unit in the x direction. So we use the term vectors. For many students, it is a common term who are doing transformations, but for some it could be tricky. So let me see that along the x direction we are taking something which has a magnitude of 1. Okay. Since it has a direction also which is along the x-axis, we also call it a vector. And magnitude is 1, so I'm calling this a unit vector. So it does, and we normally designate this by letter I, a unit vector in the direction of x-axis, right? So for some of you, let this be the concept to begin with. And then along this direction, which is y for us, we again have a unit vector which we say j. So if I say j cap and I cap, that signify unit vectors as shown here. So the thing is that we want to now rotate by an angle of theta. So that means that if this is my vector, or let's say, a position along the x-axis, and if I rotate it along theta, right, the same thing, so that is the angle theta. Then what coordinates do I get? So that's the whole idea. If you can identify that, then the job is done. So getting back to trigonometry, we could always write these coordinates since it is in terms of rotation about an angle. So basically we have to look into trigonometry. Correct? Now there you know that if this is 1, then how much is the x value of this point? Well, it is 1 times cosine of theta. So I could write this as cos theta. Correct? How about the y value? I could write that as sine theta. So what I get here is my new location after a rotation about origin by an angle of theta. Is that clear? Now, since I got it for this position moving from along the x-axis, looking into the concepts which we have learned, it corresponds to values of a and c, right? So we get this as cos theta and this one as sine theta. Does it make sense to you? It is as simple as that. As simple as that. Correct? Now, let's look into the other value, which is along the y, which I'm saying j cap. If I rotate that also through an angle of theta, then what is this new location? Well, if you look into this, then basically this angle is that much, right? So it could be written as 90 degrees, which is this angle, plus theta, right? So it is that much of angle. So the new position here could be written as, let me write down here, as far as the cosine value is concerned, it will be cos of 90 degrees plus theta. And as far as the sine value, the y value is concerned, it will be sine of 90 degrees plus theta. Is that clear? So that is going to be my new position after a rotation of theta. Now what is cos 90 plus theta? Well, cos 90 plus theta can be written as minus sine theta. Perfect. right? So that could be written as minus sine theta. Cosine is negative in quadrant 2. As far as sine 90 plus theta is concerned, it could be written as positive cos theta, right? So that is just to remind you of co-function identity. Correct? Which is very simple to understand. So let me just take a second to do that. So if I have a right triangle, and if one angle is theta, the other one is 90 minus theta, correct? So sine becomes cos, cos becomes sine. So simple as that. So that is what you get. And clearly, if that is my new position after rotation of theta, then B and D should be what? It should be minus sine theta and cos theta. Got it? So that is how we actually get our matrix which can perform the rotation about the origin by an angle of theta. Is that clear? So simple as that, correct? Now, you will be reminded of the formulas which we use in trigonometry about the compound angles, right? So we have a formula which says cos of A plus B is what? Cos of A plus B is cos A sine B minus sine A cos B. And how about sine of A plus B? That is sine A cos B plus cos A sine B. Now these formulas are also referred to as rotational transformation, right? So the word you can connect with. Perfect. Now let's see what happens if I perform this operation of the newly found transformation matrix, which is cos theta minus sine theta cos theta on any general value x and y, correct? So we took a point here, but we could have taken any point xy. So in that case, the result will be what? The result will be x times cos theta minus y times sine theta. So we get a 2 by 1 matrix, which will be this, right? Or x times sine theta plus y times cos theta, right? So if you look into this, a general point xy instead of taking 0, 1, right? So any point xy, so let me just generalize this. Okay, so I'll sketch a new one somewhere here. So think about it. If I have a point here, which now is xy, right? So, and if I move this by some angle theta, for example, let's say theta, right? So we get a point here, right? Let's say x dash y dash as the image. Then that is how their values will be related, correct? So that is how they will be. Now here, when I say xy, then this is x cos of alpha. Let's say this angle was initially alpha, right? So in that case, you will see that the value of x basically is cos of alpha and the value of y is sine of alpha. Substituting these here, what do we get? Let me write here. So the right side I'm writing here. What do we get? X will be, I could say r, if r is my length, right? So r times cos of alpha times cos of theta minus r times, so y is sine alpha, right? R times sine of alpha sine theta. And that becomes r times x values cos alpha, right? Sine theta minus r times sine alpha cos theta, correct? Plus, this is plus. So if you look into this formula here, that reminds you something, right? So r is common, we get cos alpha cos theta, sin alpha sin theta, right? That means we have cos a plus b formula here, alpha plus theta, correct? So I could write this as, let me squeeze it in, r times, so I can take r outside also, but you understand what I'm saying, alpha plus theta, and the denominator is the sine a plus b, alpha plus theta, right? So that is the result. So clearly we have done a rotation of theta on the initial angle of alpha using this matrix. Is that clear? Perfect, correct? So for any point in this plane R2, so any point on this plane can now be rotated over this transformation 2 by 2 matrix, which is cos theta minus sine theta times sine theta cosine theta. Is that clear? So let's take one example and see how easy it is now to get new points after transformation, or rather rotation about an origin by any angle for that matter. Perfect? Does it sound interesting? Beautiful? So let's take up an example now. So here is a question for you. Find the coordinates of the point 3, 4 after counterclockwise rotation of 60 degrees about origin. Now that is important. So all this, when we talk about linear transformations, we keep origin at the same place, right? So about origin, right? So what we discovered just now and understood was that the transformation matrix which does this rotation is cos theta minus sine theta, cos theta, correct? And what are we given? We need to find the image for 3, 4, correct? That is what we need to find. So one of the approach could be, let's look into the angle which is 60 degrees. Now, so here is my 60 degrees triangle. So I'm saying this is 60 degrees for me. So the sides are 1, 2 and square root of 3. So in this triangle, we know what is cos of 60 degrees. Cos of 60 degrees is half, and sine of 60 degrees is square root 3 over 2. Correct? Now since we have theta of 60 degrees, I'm going to replace this with 60 degrees and then its value. And then we'll find the new points, correct? So we could write this as cos of 60 degrees minus sine of 60 degrees, sine of 60 degrees, cos of 60 degrees, over the point which is 3, 4. Now, cos of 60 degrees is what? Cos of 60 degrees is half, so it is half minus square root 3 over 2 for sine of 60 degrees. So this will be square root 3 over 2 and that will be half. So that becomes your transformation matrix. Is that clear? And now we'll get the new points. So half times 3, so we get half times 3 minus square root 3 over 2 times 4, right? So that's 1 x coordinate. And then we get square root 3 over 2 times 3 plus half of 4. Those are the new coordinates, right? So we got our points, the new points after transformation. So basically they are what? So we can just do simple math here. I'm not cancelling anything. I'll just take 2 as a common denominator. So I'll add 3 minus 4 square root of 3, right? That's the x coordinate. The y coordinate will be 3 square root 3. The common factor is 2 here plus 4. Okay, so that's what we have. So after the transformation, the new points, we can say x, y, are what? These are my new points. 3 minus 4 square root 3 over 2 and let me write here 3 square root 3 plus 4 over 2. Is that clear? So now, using this transformation matrix, 2 by 2 matrix, you could actually find the new coordinates for any point in this plane R2. Is that clear to you? See how useful it is. Amazing. So that is how you do linear transformations when we're talking about rotation about origin by any angle theta. I hope that makes sense. So you can try out with any angle. So if the angles are like, let's say 75 degrees, you can use the calculator and then calculate your values. I hope that makes sense. Feel free to write your comments, share your views, and if you really like and subscribe to my videos, that'd be great. Share my videos with your friends and keep posting your interesting questions. Thank you and all the best.